Okay, so we've been talking about classes of compounds and classifying reactions. So the ones we've talked about so far are oxidation reduction reactions, right? And what were the types of oxidation reduction reactions that we had? Synthesis or combination, decomposition, and single replacement, right? So those are the ones that we've talked about. So what I'm passing out right now, this is also on campus for you. This you can use for your homework, you can use this for your quiz, you can use this for your exam. And you feel free to write all over it, it's fine. But what it is it has all of the different reactions that you might see, and they're classified as just talked about. You can see that the very first page has combination, decomposition, single displacement, and combustion. Those are all of our oxidation reduction reactions. So everything on this first page is also an oxidation reduction reaction, right? And so what you can see is, so even the ones we did in the lab, you can find on this page. So for example, if you have like, let's do like, what if you had calcium plus oxygen? What kind of reaction would we classify that as? Combinations, because it's two things, right? So now look under the heading of combination in your reactions handout there. So you look at combination synthesis, and then you look for one. So calcium, we would classify this one as a metal, right? And then this is obviously just oxygen. So look for the rule that says metal plus oxygen. Yeah, metal plus oxygen. So it's like the fourth one down, it says metal oxide. So it's gonna make a metal oxide. So you see how these rules work? What if I did this one? What would we classify that reaction as? The one on the top. Is it going to be synthesis, decomposition, single replacement? Decomposition. Does everyone agree? Because it's one thing. The only option is it has to come apart. So now you look under the decomposition here and you look for one that matches this. So calcium is a metal, right? And what polyatomic ion is that? Chlorate. So we look here in decomposition. Oh, does anybody see a rule? Look at the second rule on decomposition. Metallic chlorates. Does everyone see it? Mm-hmm. Number 2, it says metallic chlorates decompose into what? Metallic chloride. Okay, a metallic chloride and oxygen. Okay, so what's our metal in this case? Calcium chloride. And what does it decompose into? Calcium chloride and oxygen. Okay, what do I need to do to fix this one? CaCl. But we have to balance these charges, right? So calcium's charge is what? +2. Chloride's charge is -1. So what do we need to do? Put a 2 here, right? That's what we just did in our exam. And then what about this oxygen? What do I need to do with this? Add a 2, right? And so the next thing that we have to do is balance the reaction, right? And so that's how you can use this sheet right here. So you can use it to predict all the products of your reaction, right? So you don't need to memorize the rules. They're all on here. So every rule. So we'll practice with these. Okay, so the ones on the front page of this are all oxidation reduction. Okay. Wait, let's do one more just so you can see this. How about iron oxide plus sodium. Oh, that would be a fun reaction. What would we classify this one as? And this was a single replacement. What's giving it away that this is a single replacement reaction? Yeah, this is all by itself, right? So when you see the sodium all by itself and then you see a new compound, it's a single replacement reaction. Okay, now look at your sheet. What does it say under single replacement or single displacement? What does it say? Yeah, it says C activity series. And so then flip it over and there is the activity series for you, right? And so that helps you know, like, what do I do here? Oh, C activity series. Okay, so will this reaction happen? So again, the question we're asking is sodium going to replace iron or is sodium going to replace oxygen? Iron, because positives can only replace positives. So the question is sodium stronger than iron? So we look here, and is it? It is. Okay, so that means that iron is all by itself, and sodium gets to be with oxygen, right? But then we have to look at this. Is this one done? Sodium oxide, is that one done? It's not done, right? Because what's oxygen's charge? -2 and sodium's a +1. So what do we need to do here? Put a 2. Oops, on the sodium. 2 on the sodium, right? So that's what I mean, by the way, when I said that nomenclature never goes away. Nomenclature never goes away. It's like here forever. Yes.
So you're just balancing that.
Yep, and then you balance it. That's the nice. Yeah, all I did was balance these charges.
Okay.
Yep, same thing here. All we did was balance those charges. Yeah, same thing you did in the nomenclature lab when it said like sodium oxide, and then you had to write Na2O.
But there's still one more step.
Yeah. So our next step that we learned last class is now we have to balance this. So to balance this one, that means we have to put a 2 in front of the Na, and it's balanced, right? So I just balanced this. I put a 2 over here in front of the sodium, right? So that's our new step. And so I just wanted to show you this little piece of paper. It's on Canvas for you also, but you can use this for your homework. You can use this for your quiz, and you can use this for your exam too. And if you look on the back, we have our activity series and then the solubility table, and everything's on here. Okay. So we're going to be using this just so you can kind of see how everything works. Okay. So now, well, that's not what I wanted to do. Nope. I learned how to fix this yesterday. So now, why do you keep doing this? There's these little things that pop up, but they don't always pop up. I give up. It's like there right now, and then I touch it and it goes away. Oh, there. Okay, so now what we're gonna do is we're gonna look at the back page of this. So what we did last class was we looked at all oxidation reduction reactions, right? Now we're going to look at double displacement reactions. So if you look at the back of your handout, you'll see there's double displacement and gas producing reactions. Those are the ones we're going to look at today. So double displacement reactions include precipitation reactions, neutralization reactions, and gas forming reactions. So those are the reactions that we're going to look at today. Okay, so double displacement reactions. In a double displacement reaction, check out our reactants. So you see how this one starts with A and this one starts with C? In the products, A still stays first and C still stays first. But what happened to B and D? They switched. So in a double displacement reaction, what happens, I should probably put this here, is the second ones or the anions switch places. So whoever's first stays first and whoever's second switches places. So it's a double displacement because two things are switching, right? In a single, only one thing switched. So in a double, two things switch places. And so we can tell these double displacement reactions will either form a water or will form a precipitate, or we might form gas. And so those are going to be kind of the double displacement, the ones that we're going to see as we go. And then we'll talk about your lab as we do this too, just like we did before. Okay, so let's look at some of these double displacement reactions. So the first one we're going to look at is a precipitation reaction. So a precipitate is when a solid forms. So we start with two aqueous solutions, two liquids, we pour them together and we make a new solid. So you can see here, look at our state. So we have barium chloride, sodium sulfate, and then this is our solid, which is barium sulfate. So this white stuff in the beaker right here, that's barium sulfate. And then we also just have sodium chloride. So a precipitate means that something new has formed. Okay, in our lab, did anything new form? So we had copper 2 sulfate plus sodium hydroxide, right? And you got a new solid that formed. Okay, so let's try to write that reaction. So if copper stays first and sodium stays first, what's going to happen to the sulfate and the hydroxide? They're going to switch. So then we see the OH goes with copper and the SO4 goes with sodium. Okay, now, are those charges balanced? What is the charge of copper? Yeah, how do we know copper's 2? Because copper and copper sulfate is 2, right? This is -2 and this is +2. Again, those polyatomic ions, do you see how they're never leaving us? They're never leaving. They will be here forever. So if copper is +2 over here, copper is also +2 over here. These are not oxidation reduction reactions, meaning their charges and oxidation states never change. So whatever it is in the reactants, it's the same as it is in the products. Okay, so how do we fix this one? Yeah, CuOH2. Because it's copper 2 hydroxide. Okay. Okay, how about sodium sulfate? Yeah, what is the charge of sodium? +1. What is the charge of sulfate? -2. So how do we make this correct? Na2SO4. So just like we did in that nomenclature lab, we have to do that same thing again. Okay, so we actually have to balance the charges of each of these. Now, when you mix these together, one of these made a solid and one of these didn't. So look at that piece of paper that you have that I gave you. Do you see this thing called a solubility table? So what we can do is we can look at this solubility table and then we can figure out which one is or is not soluble. But this is a very small solubility table. So, yep, this one's on here. So, okay, so one of these is a solid, one of these isn't. So what do we see here? So what you do is you look through here. All sodium, potassium, and ammonium salts are soluble. Oh, that's sodium. That means it's soluble. Soluble is AQ, right? So when you see the word soluble, that means aqueous, not a solid. Okay. Okay, nitrates, acetates. Do you see any nitrates or acetates? We're looking for this one right here. We're looking for the copper hydroxide. Chlorides, bromides, iodides? Nope. Sulfates? Nope. We already just talked about that one. That's soluble. Carbonates, phosphates, hydroxides. We see a hydroxide. Oh, we shall keep reading then. All carbonates, phosphates, hydroxides are insoluble, except we don't have any of those exceptions. So that must mean that this was our solid. So insoluble, that means it's a S or solid, right? So solid means S. So this would be our insoluble. So when you mix those two things together, the new thing we made was copper 2 hydroxide. That was our solid. Okay. And so when you look at your double displacement, so if you look at your double displacement here, what's the very first thing it says? The solubility table, right? So usually in double displacements, if it's a precipitation, see solubility table. And that's how you use the solubility table. You just kind of keep reading it through until you find one that has something to do with something in your reaction. And then you figure it out from there. Now, oh, don't drop that. That's a really nice one. Now there's a ton of different kinds of solubility tables. So I'm going to show you. So the one you have here, this is the one we'll use on your quizzes and your exams. And I'll even have it on your final for you. But the one on active is different and the one in your book is different. If you look online, they're different. So there's all different solubility tables. So we're going to look at some of those so you can kind of get used to looking at all the different kinds. Okay, so what is solubility? It's just the maximum amount of concentration of a substance that can be achieved. So it's like the amount we can fit in. So like think of it like iced tea. So if you have 1 packet of sugar and you put it in iced tea, does it all dissolve? What? Does 6? No. Right, you can put 6 in, but you can stir and stir and stir and stir. And what are you going to see at the bottom of it? Sugar, right? So there's only a certain amount of solubility, and eventually, not all the times, but you're going to have some sitting on the bottom, right? So that would be when we had insoluble, right? Okay, so substances that have a relatively large solubility, we call them soluble. A substance will precipitate when the solution conditions are such that the concentration exceeds its solubility. So when we added our 2 solutions there, we exceeded the solubility of our copper 2 hydroxide and it precipitated. And precipitate just means that it forms a solid. So substances that have low solubilities are said to be insoluble. Insoluble again means a precipitate will form. So again, if it's insoluble, it will have a solid after it. That's what insoluble. A precipitate again is insoluble. So these two mean the same thing. So a precipitate and insoluble are both solids. If something is soluble, again, that's going to have an AQ after it. So soluble will always say AQ. Insoluble or a precipitate will always have a solid. You good with those differences? Because they're going to become really important in a minute. Okay. Okay, here's another example of a solubility table. So again, they're all a little bit different. Some people really like this one. This is the one that's in your book. So you can see here, soluble compounds. Soluble means S or AQ. AQ. So these ones are all AQs. That's supposed to be a Q. But then if you go down here, it says insoluble compounds. So what are these going to be? Yeah, these are S's. And now if you look over here, this one says insoluble exception. So these are going to be S's. Maybe if this will write. No, I want to write solid. And these are soluble exceptions. So these ones are AQs. Okay, so let's look at how we read this. So soluble compounds contain group 1 metal cations and the sodium atom. And then you go over exceptions. None. The halide ions. Halide. What group is that? Halogens, right? Which is group number 7. Now see how all this just keeps coming back? So group 7 is soluble. They're all AQs, except if it's a group 7 with Ag, Hg, or Pb. So that would be like, let's say like chloride is a halide. that's going to be AQ. Everything with chloride is going to be AQ except for AgCl, Hg2Cl, and PbCl. Does that make sense? So they're all soluble except if it's got Ag, Hg, or Pb with it. So that means like NaCl would be soluble. It would be AQ, right? No, go back. It has a mind of its own. So NaCl would be AQ. Okay. Acetates, bicarbonates, and nitrates are all soluble. Are there any exceptions? Nope. Sulfates. Anything with sulfate, again, here's what I mean about those polyatomic ions, right? They're just always here forever and ever. It's soluble except if the sulfate has Ag, Ba, Ca, H, so a bunch of exceptions. So this would be like, oh, I don't want to. This would be like barium sulfite. Sulfate would be a solid, or calcium sulfate would be a solid. So are you seeing how these exceptions work? Yes. No, you're going to have this. So you're going to have some version of this. The one that I usually put on the exams is this one that's on here because it's the one that you'll be using in your quizzes and stuff. Now the next one, these are all insoluble. So this means insoluble. So if there's a carbonate, a chromate, a phosphate, or a sulfide ion, it's going to be insoluble. They're all going to be S's. But exceptions, if it has a group 1 or ammonium, it's actually going to be an AQ, right? And then here's the hydroxides are always insoluble, except if it's group 1 or barium for some reason. So we're going to be using this to predict when we have a precipitation reaction, which one's going to be solid and which one's going to be aqueous. All right, so we're going to practice with this. Okay, so I put this on here because dissociation, we've talked about dissociations, but we're talking about them more. We're going to talk about this again because some people were confused on this. So when we did electrolytes, we talked about dissociations. We said ionic compounds dissociate. Or molecular compounds don't dissociate. So in this case, if it has an AQ after it, they all dissociate. And again, all dissociate means comes apart, right? So why does it keep doing this? I know it's because whenever I hit the keyboard, something in the keyboard makes it like get giant and not touch it. So when this comes apart, there's 1 calcium and 2 chlorine. So it comes apart into Ca2 plus 1 chlorine plus the other chlorine. But when we combine the chlorines together, we get 2 chlorides, right? So that's why it's 2 chlorides, not Cl2. That's very, very different. That's chlorine gas. That is very different, right? So this is what dissociate means when it comes apart. But when we look at our solubility table, no, I want to go backwards. When we look at our solubility table, that one was AgCl. Is that a solid or is it aqueous? Solid. So we look here and says, oh, the halide ions are soluble except if it's got Ag. So that means it's a solid. If it's a solid, it does not dissociate. So solids do not come apart. So aqueous solutions do come apart. Solids do not come apart. And we can use the solubility table to figure that out. Okay, so let's try this one. All right, what is this gonna make? So if we had lead 2 nitrate and potassium chromate, what's this going to make? So first of all, if we classify this reaction, what would we classify it as? It's a double displacement. You can see it's a double displacement because you see how this is a compound and this is a compound. Just think both of these things were in your nomenclature handout, right? So both of those things are from nomenclature. So that makes it a double displacement. So in a double displacement, whoever's first stays first. Okay, so that means when we balance this, no, stop. Stop. So when we balance this, we have who's going to stay first? PB and K are going to stay first. Now, quick question. Why is this 2 right here? Why is the 2 here? Because of chromate, right? Because chromate's charge is -2 and potassium's charge is +1. That's why the 2 is here. Now, we don't know if we're going to need the 2 here because the reason we put the 2 was because of chromate, but potassium's not going to be with chromate anymore. So we don't know if we need a 2, right? Why is this 2 here for nitrate? Because lead's charge must be +2 and nitrate's number 1. But again, we don't know if we're going to need that 2. So moral of the story here, don't take over these subscripts, right? Don't take over these subscripts because we don't know if we're going to need them. We might need them, but we might not, or we might need different subscripts. We don't know. But now, will we take over the 4 from chromate? Yeah. How about the 3 from nitrate? Yeah, we keep the polyatomic ions the way they are. So if it's a polyatomic ion, we never change its name, we never change its formula. So keep your polyatomic ions as you go over. Okay, so if we keep those polyatomic ions, who's going to go with lead now? Chromate's going to go with lead, and who's nitrate going to go with? Potassium. So this is step 1, which we say is called exchanging the ions. So it's taking those 2 and switching them. But again, never take the subscripts unless it's a polyatomic ion. You just leave your polyatomic ions alone, right? We never change the name, never change the formula. So these are our products. Okay, so what we did here is we exchanged the ions. I'll put all this up in a second. Now we have to decide, are one of these, or is one of these a solid? So let's look at our solubility table, the one you have. I don't know if the solubility table's got it on here. Here, let's go look at this solubility table. Here's this one. I'll put both of them up. You get to decide which one you want to use. Just erasing this because you don't need all this here. Okay, this one has it on there. Okay, so the ones we're looking at, yep, I already forgot. What was it?
Lead, chromate, potassium. We have the chromate, which is
PD, lead, chromate, and what?
potassium.
Okay, so we're looking at these. Okay, so let's look at potassium nitrate first. Yeah, is there any exception to nitrates? Nope. So that's one, by the way, that is one solubility rule that I always tell everybody to memorize. All nitrates are soluble because we use nitrates all the time. And so if you have that one memorized, you're like, that one's soluble. We're good. So this one is going to be soluble. So what are we going to put after the KNO3? An AQ. Okay, now let's look at lead chromate. Where are chromates? Ah, here they are, chromates. They are insoluble. Here's the exceptions. Do we have one of those? And it's not ammonium nor group 1. So that means that lead chromate is going to be a solid. So this is our solid, and this is our AQ. Now, do our charges balance here? Yeah, because lead's a +2, chromate's a -2, right? Potassium's a +1, nitrate's -1. So we're good. right? So you still have to, just like you did nomenclature, when you put two elements or a polyatomic and an element next to each other, you have to make sure their charges are balanced. So if you look here at the second page of your sheet I just handed you, step one, write the formulas. That's what we did, right? Here's your formulas up there. Step two, classify it. We said, this is a double displacement reaction. Step three, find the rule on the sheet, right? R said C solubility table. Balance the charges. That's what we just did right now. Balance the charges. And then you have to balance the reactions, and then you add the states. So this kind of helps kind of bring in your brain of like what you need to do every single time. And again, you get to use this for your homework and your quizzes and your exams. Kind of helps remind you.
I think we still need a balance.
Yeah, we haven't gotten that part yet. Yes. So the chart has more. So the one on your paper is like more, is super condensed.
Okay.
Yeah, yeah. So, and you'll see if you look online, if you go and you Google like solubility table, like this one this one here is condensed also. So they're huge. So we're just taking little pieces of them. So the ones that you have, and I think this one's a bit more complete, but if I gave you, for example, the one on the piece of paper for your like exam, I would only ask questions that you could use, that you would need that solubility table for.
So for our example,
You can write all over it. If you write too much on it, I'll just give you a new one, but feel free to write all over it. Yeah, especially because you're going to be using this for your homework and your quiz. Feel free to write all over this one. It's fine. I can just give you a new one. Okay. So now, is our reaction balanced? No, because we've got 2 Ks here, but only 1 K here. So can I do this?
no.
Can't do that, right? All I can do is this, right? Now, is it balanced now?
Yeah.
Oh, it is. So we're done, right? So see, that one was a pretty simple balancing. Not all of them are.
Does it also double the NO3?
It does.
Okay.
Uh-huh.
Okay,
Yeah, so
perfect.
this 2 says there's 2 Ks and there's 2 NO3s. So it kind of distributes through the whole thing.
Okay.
We wouldn't need to put the lead here. So there's only 1 lead here and 1 lead here. And so because this charge is plus, nope, stop. I can't make it go away. It's got such an attitude. It won't let me go. It won't go away. Okay, so because this charge of lead is +2 and chromate is -2, that's why we don't need to put a 2 below lead. Yeah, so we always have to kind of keep an idea of what their charges are when we're doing this. Okay, so let's go through that whole thing again. So the first thing we did was we exchanged the ions. So we flipped the 2 in the back, right? So we took this one and we took this one and we flipped them. That's what we did first. Then we balanced our charges. Well, they balanced. Again, balancing the charges means checking that this is a +2, this is a -2, this is a +1, this is a -1. That's what it means by balancing the charges. So we don't need to do it in this example. The next thing we have to do is we balance our equation. That too was supposed to go right here. Ignore that one. It went the wrong place. And then we have to determine if it's soluble or not. And so we looked at our solubility table and we figured out that indeed lead chromate was solid and potassium nitrate was aqueous. So when we're doing a double displacement reaction, it's a bit more work than the other reactions we did last time. They're a little bit more work. Okay. So now what we're going to do is we're going to break this up in even further. Okay, so when we talk about these double displacement reactions, do you see how this is a solid? Okay, so what made this be a solid?
The chromate.
The chromate and the lead, right? The chromate and the lead made this a solid. So what we're going to do next is we're going to figure out what is actually happening in this reaction. So we're gonna find that we have spectators and we have ones that are like actually parts of this reaction. But I feel like this is a good time to take a break. So let's take a break, like 15 minutes.